Okay, good afternoon everybody, welcome along. So last week we spent the time looking at time value of money, but we were looking at single cash flows. So that's just putting our amount of money in the bank today, how much is it worth at some point in time in the future, and then we rearranged that same formula and we looked at present values, which is saying, hey, we're going to receive this amount of money in the future. What is it worth to us today, given that we will be exposed to inflation, we could always earn a return, so all those things need to come in to our calculations. What we're going to move on to this week is still time value of money, but in Chapter 5 we now start looking at multiple cash flows. As you'll see from the first few slides, we could use the same formula that we looked at last week, but just repeat it many times. And if you're looking at, say, a 25-year mortgage, monthly payments, that's 300 different calculations you've got to do, and that becomes very laborious. So thankfully there are some formulas that we can use and apply that do it all in one step for us. So they are simplification formulas. So we'll be looking at those different aspects. Just to recap on what's coming up or has been important this week. So the main thing there is quiz 2 on time value of money. So there's just a little bit of a chat around here. I don't want to be a stickler for this, but it does get captured in the recording, and it makes it difficult for those that are watching at a distance when they're listening to the recording. So if we could just keep the chatter down, please. Thank you. So the main one here is quiz 2. It's not due until the 21st of April. And the reason for that is we've got Easter coming very early. So Thursday next week will probably be your last class for the first part of the semester. Then you'll have a couple of weeks off and you'll come back. So normally it would have been, the test would have been next weekend, not this weekend but the following weekend, but that's right in the middle of Easter, so we can't have that, and we're not supposed to have assessments due in the actual study break. So that means that it's pushed out further. The nice thing about that though is it can work in your advantage in the fact that you have extra time, if you want to, study for that piece of assessment. So not only for the quiz, but also test 1 is due at the same time. Remember, the quizzes, you can go and do them whenever you like. You can do them already if you want. And please don't leave it until the last minute and then attempt the test 1 at the same time. Use it, remember, these quizzes as your study, part of your study process. Figure out what you don't know, learn that material, go back, repeat, and so on. Any questions about on anything that we've looked at? Any administration questions? I will be providing more information about the test probably next week. I'll send out a post through Stream. There is also a mock test, which is like a mock being, it's not the actual test 1, but it's similar to test 1. Typically, the mock test, I actually put in more time value of money questions than what you would get in, say, the actual test, and the reason for that is that's the area that most people struggle in, so testing yourselves a bit more on that. And that's just really just for you. You can do it if you want, you don't have to do it. It's just a practice test, but it'll give you an idea of sort of what it's like. In these quizzes, you've been used to 12 questions for each one of the quizzes. From memory, I think it's 24 questions because it's 1 hour long. So you basically twice the number of questions, but it covers 4 weeks material rather than just 2 like the quizzes do. So any questions? Okay, so just like last week, we're continuing on looking at the tools learning outcome, the tools of finance, and in particular time value of money. Next week we will touch on risk and return. So the first few slides, as I mentioned, just really pick up and recover some of the material from last week, looking at last week's single cash flow formula. So calculate the future value of a cash flow stream being more than one cash flow. What we can do is actually apply last week's formula, which was the future value equals present value, and then the time value of money stuff, R being the interest rate, N being what year does it occur in. So we do that for each one of the cash flows that we're looking at, and then we just add them all up. The same with present value. We would find out the present value of each one of the cash flows and then add them up. Okay, so that's how we could take last week's formula and apply it to these multiple cash flow settings. You've got more than one. So this is just really just a note for the textbook. The textbook, when it talks about these multiple cash flows, it talks in the formulas, rather than having FV or PV in the formula as the two above do, it has C for cash flow. It's the same thing, and you can just use the same formula that we used last week. You don't need to put this new letter in there at all. It doesn't make any difference. So we're going to, and I'm going to run through the first two examples reasonably quickly because it's really just applying what we looked at last week. So by all means come back and revisit it when you've got time, but I'll run it through it at a speedy pace, just showing you the process rather than actually doing the calculations. So Kaylee plans to travel to the UK in 3 years' time, expects to save $1,500 at the end of year 1, $2,000 at the end of year 2, and $2,500 at the end of year 3. If she earns 4.5% per annum, how much will she have saved in 3 years' time? So once you start dealing in multiple cash flows and more complex situations, it's often a good idea to draw a timeline. It just helps you visualise what's going on. And in fact, I'll pick this up and develop it more in next week's workshop. When you're dealing with complex questions where you might be having to solve something that then becomes the input into the next part of the calculation, really does help to have this timeline. So all of the timeline is 0, 1, 2, 3 for 3 years of cash flows that we've got here, and then just putting in what the cash flow is. So in year 1, 1,500, 2, 2,000, 3, 2,500. We want to know how much, or Kaylee wants to know how much she has when she leaves to go to the UK at the end of year 3. So that 1,500 here, we can actually visually see now that 1,500 she deposits at the end of this year. It'll be in the bank account for 2 years. All of year 2 and then all of year 3. She's leaving at the end of year 3. So the 1,500 will end up with 2 years of interest. And this is where a timeline you can quickly see, and you can use your finger to do the counting if you want to, how many years compounding there is. So it becomes much more visual than just trying to think about it clearly in your mind. So all as we're doing is taking last week's formula, the present value one, and this should already be worked out on the slides there. And its R is 0.045, and it's for 2 years because it's going to be in the account for 2 years, as we said. So we end up with that will have a total value of $1,638. So an extra $138 she's going to earn based on that deposit and interest over the next 2 years. So that's the first year's cash flow sorted. Then the 2,000 will only be in the account for 1 year, so it'll only earn interest for 1 year. So then we add that one, and at 4.5%, so she's going to earn $90 in interest, so that'll be worth $2,090 at the end of year 2. And then the last one, she puts it in basically the day she leaves. She's got $2,500 extra in the account. but that's had no time to earn any interest. So it stays at 2,500. What she wants to know is how much am I going to have when I leave? So we can now just add them all up. So she's going to end up with $6,228. So with these multiple cash flows, we can just apply this formula here. The nice thing about this is actually this is what we have to do and the method we have to apply if the cash flows are different every year. Because what you'll see is when we get to these fancy formulas that do multiple cash flows, there's something about them that's the same every single year. Either the amount's the same or they are growing at the same amount. Whereas this is sort of all relatively random. So we can do the same for present value as well. So we've got here Casey is being offered an investment that promises to pay $5,000 at the end of year 1, $6,000 at the end of year 2 and $7,000 at the end of year 3. Interest rate's 10% and the cost of the investment is $16,000. What that is saying is she's going to have to, Casey, could be a boy, they are going to have to deposit or pay $16,000 today, and then this is the cash flow returns that they will get from that investment. So 5,000, 6,000 and 7,000. And that they want to earn 10% return on this particular investment. So in your notes, that should already be there. So all as you're doing is applying last week's formula 3 times. So you're taking that formula and you're saying, okay, for the first year it's going to be 5,000 as the future value, second year 6,000, third year 7,000. And then 3 calculations, which allows you then to go through and add them all up. So Casey is going to potentially invest, or trying to figure out whether they should invest, $16,000 today for something that's only worth to them, if they need this 10% return because of the risk of the investment, it's only worth to them $14,700. So should they invest in this or not? Anybody? Would this be a good investment for them? No. And that's the correct answer. No, they should not invest. The reason for that is actually it's not earning what they want to earn. Later on, when we start looking at business finance, we'll come across something called a net present value. Same sort of formula and same process. And what it's doing is saying, okay, we only want to invest in projects that are going to increase the firm's wealth or value. In this case, we're talking about an individual. But they should, again, only invest in projects that are going to increase their value. They're paying $16,000 for something that's only worth just over $14,000. Therefore, their value is actually going down. If they make this investment, they're losing. Or put it another way, they require 10% return. They're not getting that. They're getting less than 10% return on this particular investment. Okay, so we will revisit this type of process. I think it's around about week 9 and 10. So we'll come back to that. What I want to do though now is move on to more of these simplification of repeated cash flows, things that are consistently repeated. And we're actually, during our day-to-day lives, actually exposed to quite a few of these. Think of your rent on your house that you might be renting. Insurance is often a same amount every month that might go out of your bank account. So there's lots of things where end up being formed in what is called these repeated or regular cash flows. And there's 2 types. One's an annuity. That's the more common ones that we'll be exposed to. So rent every week, every month, or whatever it is, that's an annuity form. If you're lucky enough to have a job, then it's every week you're getting money coming in. KiwiSaver, if that's going out from your salary, then that's tends to be the same until your wages change or salary changes. So, and very common annuities is mortgages as well, and loans. The other one is perpetuities. So the difference between the two is an annuity is for a finite period of time. You get a loan for 30 years, eventually you pay it off, but it is a finite period. Very long period, but it is finite. Whereas a perpetuity, the word perpetuity comes from the word perpetual, meaning it doesn't stop. Okay, so there is no ending point for that particular stream of cash flows. We, on our day-to-day lives, are less exposed to perpetuities unless you're investing in particular types of investments. So Fonterra, for instance, they have issued something called Fonterra. They are called Fonterra perpetual notes. It's like a bond. They pay out interest, and they will, as long as Fonterra is around, they will have to continue to pay the interest on those forever. So there are things that you can buy, but a lot of scholarships are actually set up this way. So you get some wealthy benefactor comes along to the university and say, hey, I've got all this money, I want to leave some of it to the university, but I'd like to create a scholarship for, say, first-year finance students. And so what they do is they donate a whole lot of money, but they are very clear when they donate it that they're not actually allowed to use the amount that's been donated for scholarships. Actually, all as they can use is the income that's generated off those assets. So that means the assets themselves, they stay intact. And any income that's earned off those assets is then paid out as scholarships. That means that can continue to pay out those scholarships forever because the original amount remains intact. So we'll have a look at both of these. So first of all, annuities, the more common ones, at least in our day-to-day lives. Equal payments made or received with a regular frequency. And as we said, for a finite period. There is an ending point. And you've got to look at what's happening with the cash flows, because this means they fall into two different types. So, ordinary annuity is when the payments are at the end of the period. So, common examples of this would be wages or salaries. You know, you work for a week, then you get paid. It's the end of the period. Mortgages or loans. You take a loan out today, you don't make your first payment today. You actually make it at the end of the first month, or whatever period you're paying it off at. Okay, so they are called ordinary annuities. We're not very original in finance. The reason why it's called ordinary annuity is ordinarily that's what they look like. Cash flows at the end of the period. Annuities due, on the other hand, the payment is immediate, today. So, insurance is very much like this. You pay for your insurance up front. You know, you don't drive around a car for a year and then at the end of the year you pay your insurance for the previous year's driving around, you know, the protection. The insurance company wants the money first because they know if you drove around for a whole year and you didn't have an accident, well, what's the point of paying the insurance premium, right? So they have to have the money up front and then you're covered for that period. Leases are set up this way. Often rents are as well, even residential rents. we'll come back to this point, but it's just a point to note that both future value and present value annuities due are larger than their equivalent ordinary annuity. And the reason for that is the first payment is made earlier. But we'll have a look at that more closely. So, let's start looking at some of these fancy formulas. Fancy because there's a whole lot more going on in them than what we had last week. So this one is for a future value annuity. It's an ordinary annuity, so it means that the payment is assumed to be at the end of each period. So we've got the formula. FVA is the future value annuity. PMT stands for payment. It's the regular payment that you are either paying or receiving. R is the same as last week, the return or interest rate. And N is the same as last week, which is the number of years. So in example 3 we have Karen, who's depositing $2,800 at the end of each year for the next 4 years. So you can see here this is a regular amount at a regular interval. Each year, $2,800. Interest is 7.5%. How much will she have accumulated by the end of year 4? Now, we could go back and apply what we went through with the future value in example 1. Future value formula from example 1 in this lecture. Just apply that to the 4 cash flows, add them all up, we'd have our answer. Okay, so you'd have to do 4 lots of calculations and then a 5th calculation to add up all of the future values. Or we could just plug the numbers into this formula and that would give us, it would work all of that out for us. So what I'd like you to do is just, that should already be on your slides, but for those that have got calculators, hopefully everyone has, just make sure that you can see if you can get to that answer. While you're doing that, I'm going to do it on here as well, hopefully.
Yep, what do I do?
Always pays the check. Okay, so you should end up with 12,524. One of the things I like to do, because it allows you to go back and check when you make a mistake like I did before, is actually to do some workings. Now, I've done quite a few workings there, you don't need as many as that. On the slides you'll see I've done the first bit of working is plug the numbers in, which you do need to do, and then I've got one other bit of workings in there. So I've solved for everything in the square brackets. But what I would typically do myself is actually work out in the square brackets what the top part of the bit in the brackets is. So 1 plus 0.075 to the power of 4 less 1. And then in the next step I would divide that by the interest rate again to get you, the 4.47. And that allows you to go back later and check to see that you're on the right track. Any questions on that? Okay, so she will have just over 12,500 in 4 years. So we're now turning to... actually, there is one thing I do want to show you, and it's just for some calculators. I need to go back to this. Sorry. Is that easy to see it? Oh, not quite sure. You can't see that, can you? If I turn the lamp on, maybe that will help. Not at all. Okay. There you go, that's probably about as good as I can get it, sorry. Just with regard to this particular formula, and some of the others are like it as well, if you look at the formula, it's got, it's inside the square bracket, it's 1 plus r, close bracket, to the power of n, minus 1. You just got to be careful when you're entering in the numbers that you're actually entering it in as the formula is and not just a straight n minus 1. And it becomes clearer once I actually go through and do the calculation. So first of all, 2,800, open the brackets, then we need a fraction, and we've asked to open more brackets. So we're now doing the top part, 1 plus 0.075, close the bracket, raise that to the power of 4. This is where you've got to be careful, because when you look at the screen, you could just go minus 1, which is actually not right, because that's like to the power of now 3. Alright, so just got to be careful with that bit. On not all calculators, but particularly the ones where you're actually entering in the data like this. What you actually need to do is use the replay button and move out. So you'll see that it drops down from a superscript back down. Then you can go minus 1. Go down to the bottom, put in 0.075, right out to the side, and close the brackets. Okay, so just be aware of that when you're going through your calculations. It's really easy, particularly in a test situation, just to run through that quickly, because that's what the formula looks like. You plug it in, you've actually got something different. Okay, so we've now got the present value formula, so we've got some payments or some cash flows in the future. We want to know what they are worth today. So Kane estimates his uni fees will be $11,000 each year for 3 years. How much should his grandmother put in an account now to cover his fees? Very lucky to have a grandmother that would do that. And interest is 8% per annum. So, first thing you need to do is extract the information. So you're looking for things like payment. And payment is, there'll often be words around it like each year or every year. In other words, it's something that's happening over and over again. So the 11,000 must be the payment, and it's happening for 3 years, so N will be 3 and R will be 0.08. So we can plug the information in now. And then calculate that through. So we should end up with, so what this is saying is if his grandmother put 28,000 into a bank account today, he would be able to make 3 payments of 11,000 out of that and use up all of that money. And then that covers his fees over the next 3 years. So that's ordinary annuities. What about annuity due? Well, actually, all we need to do is for any of the formulas, whether it's the future value annuity or the present value annuity, we just need to multiply it, each of them by 1 plus the interest rate. Because all that is saying is everything's actually had 1 more year's. You think about a future value. You put the money in today versus putting it in the end of the year, you've got 1 year's extra interest that you're earning, right? Because you put it in today, so it's going to earn interest for that whole year first. So it's everything that you've deposited has 1 more year's time to accumulate interest. And that's why we're just then taking the original formula and multiplying it by 1 plus the interest rate. So Kane now realises that he needs to pay his uni fees at the beginning of each year. So he goes back to his grandmother and says he wants more money. How much more money does he need? So all we actually need to do is take our amount from the previous slide and multiply it by 1 plus the 8% that they're earning. So this, from the previous slide, we've already calculated all of this bit here, all the way through to here. We've done all of that calculation. All we're now doing is just taking that answer and multiplying it by 1 plus 0.08. And for that, we should end up with 30,615. So he actually needs to go back to his grandmother and say, hey, we actually need a bit more things. So if we were doing it for a future value annuity due, same thing. We could take example, the future value annuity example we had, and just multiply it by 1 plus R. That would take into account the fact that the first payment is today rather than the end of each year. So the next one is calculating annual payments. Or, it doesn't have to be annual payments, we'll start off looking at that. It could be any payment. Essentially we're solving for the PMT in the formula. So we just, and the textbook does this for us, rearranges the formula for us, so we can plug the numbers in and it will calculate payment for us. So this formula here will be calculating the payment for a future value annuity. How do we know that? Well, we know that because it's got FVA in the formula. So it's not doesn't have PVA in there, present value annuity. So it must be the future value one. So this is useful for calculating payments need to accumulate a future sum. So we know that when we want to go on our OE or some holiday or some future event, or we're trying to save up for a deposit on a house, we know what our goal is, we know the amount we're trying to save towards, we just don't know how much we need to save each year to get to that. This is what this formula does. It tells us how much we need to save each year to get to our desired goal. So the Cardigans want $80,000 for a deposit on a house in 5 years' time. If interest is 5% per annum, what annual payments should be made to achieve this goal? Okay, so they're standing here now, they don't have any money, they want $80,000 for a deposit in 5 years' time. How much do they need to save each year to get to their goal? You know, it's sort of a common sense approach is if you just took 80,000 and you divided it by 5, that's 16,000 each year. But that ignores interest, right? So they actually should deposit less than 16,000. They don't need to save 16,000 each year. It's less than that because for each deposit they make, they'll start earning interest over that period. But that's a good common sense thing to do, is that say you're in an exam and you've calculated an answer, you're not quite sure whether that makes sense or not, just do a straight, okay, well, what would it be is if they earn nothing. If they earned nothing, they would have to save 16,000 each year. But if they're earning something, that means they don't have to deposit as much each year. So, payment is equal to the future value annuity, which is 80,000. That's how much the goal that they're saving towards. R is 5%, 0.05, and N is 5. Earning interest over that period. But that's a good common sense thing to do, is that say you're in an exam and you've calculated an answer, you're not quite sure whether that makes sense or not, just do a straight, okay, well, what would it be is if they earn nothing. If they earn nothing, they would have to save 16,000 each year. But if they're earning something, that means they don't have to deposit as much each year. So, payment is equal to the future value annuity, which is 80,000. That's how much the goal that they're saving towards. R is 5%, 0.05, and N is 5. I'm just wondering whether it's the lighting. Not really helping. It's not helping at all. Ah, that's better. Can you see the zero on the screen? Yep. It's not ideal, but it's... that's better. Right, this is a different calculator. This is a Texas Instruments financial calculator. Some, I'm aware, have purchased this type of calculator, or you might be using other financial calculators. The reason why I just want to show you some of this is because there are a couple of differences with financial calculators compared to a standard scientific calculator. A couple of little weird things that go on with them. So, to calculate this, we know it's a financial calculator because it's got these silver row of buttons here. N is the number of years, PV we've seen, PMT we're working with right now, future value, we've seen those as well. The only difference is IY, which is interest rate per year. In other words, R, the return. So that's the time value of money buttons there. Not all financial calculators are exactly the same, but generally speaking, you type in the number. So in this case, it's 5 years. So we push 5 and then hit N. And now you'll see it says N equals 5. One of the weird things about financial calculators is that you enter in the interest rate or the return as a whole percentage. All of the formulas that you've come across in chapters 4 and 5, all the time value of money formulas, when it talks about 5%, you've actually got to convert that into a decimal, 0.05, before you put it into the formula. With your financial calculator, you actually enter it in as a whole percentage number. So that can create a bit of confusion when you first start using a financial calculator, because it's different to what you would do using a scientific one. So that's one of the weird things. I'll just plug in some numbers here so we know that they're trying to save to a future target. We're not told in the question they've already got money, so we have to assume they've got no money. So we put in 0 for present value. They currently have nothing. Payment we're trying to solve for. So the next thing is the future value. What is their goal? And that's the 80,000 is the goal. So future value equals 80,000. And then, depending on the type of calculator, there'll be a button that you push to get it to work stuff out. And in this version, or this calculator, it's CPT, which stands for compute. In other words, you're going to compute the answer. So you push compute, and we want to compute something. The answer we want is PMT. That's what we're trying to solve for. So you'll see there that we end up with the answer, but there's a little negative in front of the answer, which is another one of these weird things about financial calculators, actually also Excel. So with Excel and financial calculators, one of the cash flows ends up being negative, and it's to do with what's happening to your bank account. So in reality, what is actually happening is this 80,000 that they are going to use as a deposit in 5 years' time will actually be money that goes out of their bank account. So their bank account will have a negative transaction for negative $80,000 when they buy the house. So that is actually a negative 80,000 out of their bank account. So if we actually reflect that there and then we compute the payment, we get the same number, but it no longer has a negative, because what that reflects is that each year they need to deposit $14,478 or whatever it is. Okay, so it's a positive amount that's going into their bank account. After you've done a few calculations with a financial calculator, you'll just start ignoring that negative. Same with Excel as well, if you're using Excel. Any questions on payment? What about payments relating to the present value formula? This is where we actually can use it in a lot of stuff, solving our retirement puzzle, how much we need to save, how much we're going to spend, spend in retirement, mortgages, all those sorts of things. So here, suppose we have a lump sum of money invested now and we wish to know how much could be withdrawn on a regular basis until our funds are exhausted. Then we could rearrange the present value annuity formula to solve the payment. That's essentially what you're doing once you get to retirement. You say, oh, I've got this great big nest egg now. How much can I spend every year until it's all gone? First thing you're going to do is estimate when you're going to die, which is always a bit of a trick, but that's essentially what you're doing when you sit down with a financial planner, is they sort of figure out that sort of for you. Don't live too long. So we could also use the same formula just for mortgage payments, loan payments, car loan payments, hire purchase agreement payments, those types of things. By the way, I do apologise, there's lots of formulas in this particular, and lots of calculations in this particular lecture, which you'll find when you read through Chapter 5. It's very heavy in the tools of finance. Thankfully later on, actually next week's a lot of calculations too, but later on we start applying these tools, which is a bit more, it's a bit more interesting, I think, when you're applying these things. But you can get the idea of sort of where they're useful and will be useful in your day-to-day lives. You know, not everyone here is going to carry on and do finance, but chances are you're going to have a loan at some stage or other, whether it's a loan for a car or a house or whatever it might be. We're also hopefully all going to save some for our retirement as well. So these are annuities that we will be exposed to. We can figure out how much we need, how much we're going to be able to spend, those types of things. So example 7, you wish to buy a house and will borrow $500,000 for 25 years at an interest rate of 6%. What would be your annual payments? So, bringing up that formula again. So the present value annuity, that's what it's worth today, is the value of the loan. That's what you're borrowing, $500,000. Or put it another way, a very scary amount of money. How long are you going to borrow it for? 25 years, that's N, and the interest rate, or the money that the bank's going to run off with, is 6% on what you owe them. Now the thing with loan payments and with mortgage payments is that when you make a payment, you now owe the bank a little bit less. So the next month, or whenever they come around to charge you interest, they can't charge you as much because you've paid a bit off your loan. So the actual payment that you make every single month for 30 years or whatever it is the same, but the amount of money that they take off as their income, the interest, versus how much is being paid off on your loan varies after every single payment. So the amount that's being paid in interest versus principal, reducing down what you owe, changes right throughout the life of the loan. And we'll have a look at that after we have a bit of a break. But if we go through, we've got $500,000 here times 0.06, which is the interest, and then the denominator is 1 minus, in brackets, 1 plus 0.06 to negative 25 years. So the top part, numerator, $500,000 times 6% gives us 30,000, and then the bottom part, work that through 0.767, we end up with 39,000. We'll just take a bit of a break there. What I want to do when we come back is actually look, say, hey, no one makes mortgage payments on an annual basis. They make them on either a monthly or a fortnightly basis. So how can we change this formula to reflect the fact that they're paying it on a more frequent basis? Okay, so let's just take a short break there, and we'll come back, we'll carry on with that. Thank you.
Can you show me how to change it to make sure my payments are the end of the period? And also, I was just reading the cash flows there, but is that
Yes, and that's where you can do those, like at the beginning we had 1,500 and then 2,000.
Yeah.
So, that's used for something called net present value.
Yeah, I did it last year a little bit.
I can show you how to do that.
Maybe.
That's probably the best.
Yeah.
It does just take a little bit of sequence to get through.
Yeah.
Right. So that's BGN there. We're going to, and it's in yellow, so the second currently set at end. I would leave it at end. Don't change it. Because what? Yeah. Most questions were based on the cash flow sheet. When you specifically say at the beginning, we'll change it. One thing I would just change for you is the number of decimal places here. So, second, format, and it's currently set to 4. You set it to 9, sounds like a lot. And then enter in the down arrow here. You'll see now it's 0. And if I go 1 divided by 2, it's 0.5. And if I go 1 divided by 3, it feels like the same. Just like an calculator.
Yeah, that's good. Alright, thank you.
Hi, I'm an extramural student. Okay. Just purely unquote. How do I get it to count?
Good question. I'll do this calculator also. Be with me. So I just do basics for fun?
Yeah. Right, I was pressing that.
Okay, cool. I'm not sure what that stands for. It's not exploded.
Okay, that's what I thought it was.
So it's this one.
So it's that one.
So if you want to do 1.1, just that,
Yeah.
it's actually the same in itself.
Yeah.
5.
So it's just,
So that's one. So it's like 10%. 5 years.
Yeah. Cool. Thank you.
And 1.1.
I'll cool. So you use that one, not that one.
Yeah, some calculators still works with it.
Yeah.
Not all of them.
Okay. Perfect. Thank you. It's been 15 years. So you.
Just be rounded. It doesn't matter. So in any assessment, if you were asked to write down your working, then I just see working, then I'm making working something like that. If it's online, you've got to type in your answer. There is rounding options that are allowed. And it's typically 1%. In this case, that would be like $140 each side. That would allow rounding. So it would well and truly capture that amount. And if it's multiple choice, then the next closest answer would be several hundred dollars. So it's not going to finance it or use this course in the future. Just that. So, yeah, best thing is to try and leave it in your calculator around the end. It doesn't matter.
Please go through the financial calculator.
Okay, I'm just going to change it around. And now it's just so we've got $500,000 is what we're borrowing as a present value amount. What do you think the future value of the loan will be after 45 years? So what?
So it's what, 500,000.
Basis point. Well, no, the future value of the loan. So you've actually got to put that in. What that does is just blocks out any basis. Payment, so oh, sorry. You're right. And then it's just computed.
Oh, okay, I wasn't doing that. Would that be the future value? Right. I should have mentioned that. Yeah. Also, did you see Facebook?
No.
Down 9%.
Oh, sorry. I thought you meant Facebook. Sorry.
Oh, no, cool.
Yeah, no, I don't think it
Zuckerberg's offloading.
Okay, if you could make it on the start, please. So when we finished off, we were looking at mortgage payments on a house and looking at annual payments, but nobody makes annual payments on their home mortgages. It's either, as I said, monthly or fortnightly. So how do we go about changing this amount into a monthly amount? Or alternatively, a fortnightly amount? What do we need to do to the formula in order to tell it, hey, we're actually paying it off monthly rather than annually? So, first question is, can we simply divide the yearly amount which was $39,113, by 12 for months, or 26 for fortnights. Can we do that? Will that give us the right answer? It won't. Can't do that, sorry. And the reason why we can't do that is because we are paying it off sooner, only a little bit, but we're paying a little bit off sooner after 1 month. That means the bank has less opportunity to earn interest. So that means their return is less, which means our payments should be smaller. So a good, is this number okay, is actually, if you've already got the annual payment, you could simply divide it by 12 and you go, okay, it's got to be less than this figure here. It's got to be smaller than that because the bank's going to earn less. We're paying it off sooner, every month. Still going to take us 25 years to pay it off, but after each month. So if you think about it in the previous scenario, in that entire first year, they are earning interest, the bank, on $500,000 before we make our first payment. If we change it to monthly, we only have to wait 1 month, we make a little bit of a payment, but now for the rest of that time, they can only earn interest on that lower amount. The next month we make a little bit more payment, and so on. So they're not earning interest on $500,000 over that entire year. It's a reducing amount. So what can we do? Well, this is where we go back to material from last week. There was a slide that had a title called TVM and Compounding Frequency from last week's material. And in it, we introduced this idea that if we have more compounding periods than once per year, we can adjust the formulas. So we introduced this thing called M. And M, by the way, doesn't always refer to months. It refers to the number of compounding periods per year. So if it is monthly payments, it'll be 12. If it's fortnight, M will be 26. So, the formula, if you went back to that slide, what it says is that wherever R is in the formula, it becomes R divided by M. Because we don't want to know what the interest is over the whole year, we now actually only want to know what the interest is over the month or the fortnight. The other thing we need to tell the formula, which is right out over here, is N, for the number of years, multiplied by M, how many times do we make payments each year? What that is telling the formula, how many payments do we have to make on this loan before it's entirely paid off? Okay, so it's telling the formula how many payments there is in this loan. So now what we've done is we've converted the formula now from an annual amount into everything is now based on months or fortnights if we choose to put 26 in for M. But whatever it is, whatever we put in for M, that's the period relative to how frequently we're paying off this loan. So let's have a look and see what the numbers look like. So exactly the same question, but now we're doing monthly payments. So first, we calculate the total payment periods. How many payments are we going to make before this thing is actually finally paid off? That's 25 years, 12 payments each year. So that's 300 payments we're going to have to make. The next one is, okay, for each one of these months, what is the bank actually charging us? It's 6% over the entire year, but 1 month's worth of that is actually only 6% divided by 12, which is like 0.5%. So, One thing I just want to do with your, and I know not everyone has financial calculators, so this is only affecting a few, but I just want to go back to it because there was something I should have covered which I didn't, and I'll use this example. So, at the moment in my calculator you'll see I have data, I have data already stored in here. I've still got the 80,000 from the previous question, I've still got 0 for present value, I've still got n equals 5. So my previous calculation that I've made is already stored in here. I either need to get rid of everything, clear everything back to 0, and I can do that in different calculators, will have different ways of doing it. For this one it's just second CE. But actually my preferred method, and this way it doesn't matter which financial calculator you've got, is actually you've got 5 buttons here. Make sure that you're using all 5 in every single calculation. And what I mean by that is if we look at this question here, we know that we're borrowing 500,000, so that's the present value of the loan. If we go and get that today, that's what it's worth. So present value. Our interest rate is 6%, but it's divided by 12, so 0.5% per month. 25 times 12 is our payments. That's total number of payments. And the other thing that I need to do is say, okay, I've got something now for N, I've got something for the interest rate, I've got something for the present value, I'm solving for payment. The other thing is future value. Now, if you look at the formula, there is no future value in there, but your calculator will have stored information from previous questions you've done. And if you're in a test situation, you're racing through your questions, the previous one had a future value or something in there, it's already in there, sitting in there. And you need to clear that. So what I like to do is make sure that I'm always entering in 4 bits of information and solving for the 5th. The 5th one in this case is the payment. So the 4 bits of information I need to enter in are N, IY, PV and future value. What this does for me is it forces me to go back to the question, read the question and say, is there anything in here about future value? And the question, does it mention future value? It doesn't. So it must be 0. But actually, what is the future value of all loans? Whether you borrow $10,000 or 10 million? 0. So the future value of all loans is eventually, after the 300th payment, it's actually 0. Okay, so be careful in that if you've got a financial calculator, enter in 4 bits of data, it forces you to go back and read the question to see whether there is anything there about the one that seems to be missing, then hit compute payment. So we could just do the whole formula, chuck it in like that. I actually like to, as a step-by-step process, if I'm doing this by hand, is actually work out how many payments there are, first of all, 300, then what is the interest per period, or in this case per month, 0.5%. Then put that into the original formula. So you do the adjustment bits first, plug those in. The problem with the one out the right there is you can get lots of stuff going on, and particularly if you're trying to feed it all into like an FX82 all in one go, it can get really confusing about what's going on. You should end up with $3,221. Right, and you'll see that, remember our annual payment was just over 39,000. I can't remember exactly what it was. But if we multiply this by 12, it's under 39,000. Okay, so that's that reality check, or that check, does this make sense? And yes, it does. Should be slightly lower. Another thing that's very useful, and not only just for home mortgages, but for any type of loan that you've got, is to actually figure out how much you owe after each payment. The reason why it's good for that is if you actually start tracking it, and the loan agreement allows you to do it, not all of them do, it allows you to actually figure out what will happen if you pay a bit more or you pay off a lump sum, all those types of things. And it's really good for reducing down that debt, because you're actually tracking it now. Whenever you measure and track something, you tend to get more focused in on it, and you can eat through that mortgage much quicker. So a loan amortisation is the process where the loan is reduced to zero over life, and all we're doing is having a look what happens after each payment. Easy to do in Excel, it's a bit laborious if you're doing it by hand, but the process is the same. So we need to look at the process first, then I'll show you in Excel. Payments consist of both principal and interest. So that payment of $3,221 is the same every year for 300 payments. But early on in that loan, most of that $3,221 will be interest that the bank takes off and runs away with. And very little of it actually goes off on paying off your loan. Near the end of the loan's life, the opposite is. You're paying off more interest, you're paying off more of the principal amount, and they are taking away a whole lot less of the money as interest. So we're going to show you how this works. So your notes should look like that. We're going to run through those notes, just filling in some of these blanks here. So based on example 8, where we got the payment of $3,221, the monthly payment, we're going to work out what is the balance of the loan after the first, second, third and fourth months. Which means if we went to month 4, that's how much we would have to pay if we rocked up to the bank and say, hey, just won lotto last night, here's your money for the loan, don't want it anymore. So the tricky thing here is actually working out, first of all, the interest payment. Think about it from the bank's perspective. The bank looks at it and goes, you owe me $500,000. I'm going to charge you some interest. And so they go to have a look at what the interest rate is. That's something of what they can charge. And they look at how long it's been since they charged the interest. In this case, it's months. So it's only been hasn't been any months yet, but at the end of the first month, they'll look back and say, oh, you've had this loan for a whole month. You now owe us some interest. We're going to take some money. So how we work that out is we take the opening balance of what we owe the bank at the beginning of the month, we multiply it by the per period interest, which is, the 6% divided by 12 months, so half a percent that we saw in the previous slide. So opening balance times interest per period will give us $2,500. So we make our first payment, that's at the end of the month, they charge us that. Also at the end of the month, we make our first payment of $3,221. So you can see there very quickly that most of them, we pay $3,200, but actually 2.5 of it is just going to the bank as interest. Very little of it, relatively speaking, is going on actually reducing that loan amount. Now you can think about it either from the bank's perspective or your perspective, but we need to figure out what this closing balance is. So from our perspective as the borrower, we would go, hey, at the beginning of the month we owed $500,000. Then they charge us some interest, so we now owe them $500,000 plus another $2,500. But then we make a payment. Phew, finally we're actually reducing this loan. So it'll be $500,000 plus $2,500 less the payment. Which will give us $499,278.49. So we've just paid off about $750 odd off our loan in the first month. The closing balance in the first month becomes the opening balance in the second month, because we're only talking about, tick over midnight, and that becomes the beginning of the next month. And we go through the same process. And this is where you should be able to see that the bank is now actually earning a little bit less in the second month, because we go through the same process. We take the opening balance, which is now slightly smaller. It's only $499,000 now, 278, and we multiply that figure by 0.06 divided by 12. So the 0.06 divided by 12, that doesn't change. That's the interest and the number of months, that doesn't change. But the amount that we owe the bank does. So we repeat that calculation, but based on the new opening balance, the bank will take off with now $2,496 in interest. We make the same payment, which we calculated on the previous slide, and that process now can be repeated for each year. Fairly laborious when you're doing it by hand. In Excel, becomes much quicker. So I'm just going to show you that in Excel. Hopefully. There we go. Came up nicely. I was having trouble with it before the class. So most of the information here is what we've got. What I need to do is work out loan payment, and I started showing you last week that some of these formulas are already built into Excel, and this is another one that is. So I'm going to insert into this white box here a financial formula, and it's, as you might suspect, PMT, what we're trying to figure out. And it brings up a whole lot of stuff that we've got to then put in. So the interest rate, well, it says here it's the interest rate per period. So it's not per year, but we do need to go out and get the annual amount first, and then we need to divide that by the number of periods per year. And you'll see that, well, you might not be able to see, it's very small, 0.005 or 0.5%. N per, it says, is the total number of payments of the loan. So that's just like what we were working out before, 25 years times 12 gives us 300 payments, and this is what we're borrowing, $500,000. Remember I said about financial calculators, one of the weird things is some of it's positive, answer comes out negative, same thing with Excel. And in actual fact, this represents what's happening, right? When we go and borrow the money off the bank, all of a sudden we're $500,000 richer in cash, not really richer. In cash, not really richer, but we've now got an extra $500,000 to go and spend. Okay, so that's like money coming in, but then for the next 300 months, that amount will be going out of our bank account. Okay, same process is equal to the opening balance. So this is the same process of what we just looked at on the slide, times the per period interest, which is 6% divided by 12, so $2,500. Our payment is equal to that, and because it's a negative, if I add all of these up, it should come out right. So equals. And we get that same answer. So as a check, it should be slightly lower than what you started with. If it's, you do a calculation, say in a test or something like that, and it's bigger, go back and check your calculations. That becomes the opening balance. Same process, copy that down. Yep, that's what we had. Same payment and closing balance. And once you've got it there, you can just copy it all the way down. And if we scroll now all the way down to the bottom, whoops, you'll see that once we make our 300th payment, we now owe the bank nothing. Finally, the nice thing about setting it up like this is that, you know, say after 5 months, all of a sudden you got a bit of a pay rise. You can go out and splurge it, or you could say, okay, let's try and crack this mortgage out a little bit faster. So I've got I'm getting another $100 extra a month. So, you know, say let's put another $400 on the mortgage. So we'll change this to, say, oops, need to turn on the number slots, 3,600. So we can now track what's happened. And the nice thing about this is you scroll down and eventually you'll see that it goes negative. So here, we've now paid, you know, we're paying off a little bit extra, $100 extra, it's quite a lot extra, but we have reduced from 300 payments that we've got to make now to 240 payments. So we've taken off 60 payments, which is 5 years. So we've gone from a 20-year mortgage now to, 25-year mortgage down to 20-year mortgage, just like that. So whenever if you do in the situation of, in the future of getting a home mortgage, often trying to reduce it down, the more pain you experience in the initial years, the more gain you have later. A bit more financial freedom. Any questions? We're going to revisit that, by the way, next week in one of the workshop questions as well. I just remember when I had my first home mortgage, which I was absolutely freaked out about. It sounds piddly now, but it was, what was it? I think it was $110,000. I lost a few nights' sleep on that. But I did spend as much. I tracked it sort of every couple of months. I'd go in and check it and see if I could actually pay a bit off, and so was able to pay it off relatively quickly. It doesn't really matter whether you start with $100,000 or $500,000 or whatever loan, the same idea will actually reduce it down much quicker. So we've looked at annuities. It might seem like you're paying off your mortgage forever. You do eventually pay it off. Perpetuities, on the other hand, are forever. So this is an infinite stream of cash flows. The formula is relatively straightforward. It's just the cash flow divided by R is the present value. So note that the 1 in C1, this is quite important, is actually the cash flow in year 1. The formulas, as they are stated in chapters 4 and 5, they all assume that the cash flow is at the end of the year. Ordinary annuities, the normal formula, the normal annuity formulas for future value and present value, they assume that the cash flow is the end of the year. And they're called ordinary annuities because ordinarily that's what they look like. We actually have to tell the formula something different if we want to convert it into beginning period payments. So it's the same with a perpetuity. The formula, as it's stated, assumes that we're talking about a cash flow at the end of the first year. Not today. So the first formula that assumes that the cash flow, C, is the same every single year forever, doesn't change. Whereas the formula below assumes that the cash flow is growing at the same rate every single year forever. And you'll see here G is a new thing, and that's the growth rate. So that might be like we're growing it at 2% per annum. That's what it's growing at. So, initially a little bit hard to get your head around. By the way, there's I mentioned that Fonterra has some of these perpetual notes. Will be around as long, and they will have to continue paying interest on them for as long as it's around. The oldest one I can find data on. There are older ones, but they mustn't trade very often. The oldest perpetual bond that's been issued was by the Bank of England in 1729. Sorry, not the oldest one. The oldest one I can find continuous trading data on over that period. So you can actually track the interest rates over that last nearly 300 years for England through that, because it's something that's been issued by the government, or backed by the government. They still pay out interest on those. They are perpetual. They will not stop as long as England's around. A couple of interesting things though. You see that the interest rate really rises around the world wars, particularly World War I, which makes sense because if they had lost either one of those wars, the new people coming in and controlling England would not have honoured continued paying the interest of those things. Okay, so that creates this spiking risk and therefore the return that people want to compensate for that. So what do we got? Clearly when I was writing these notes I got stuck on the letter K for all my people. Kerry wishes to set up a scholarship to pay $5,000 to the top student every year. If the interest rate is 5%, how much must Kerry initially donate? So she's looking at donating to, say, Massey, and she wants to set up this scholarship here. So initially, it's just 5,000 divided by 0.05. 5,000 is what she wants the scholarship to be each year. 0.05 is the interest rate. That means if she donates $100,000 a year, if she donates $100,000 every year, $5,000 in interest can be paid out as a new scholarship. And I'll show you how that works shortly in Excel. You can probably start to see that there. It's a little bit less clear for the next one, and then I'll show you in Excel. If Kerry decides that the payment should grow by 2.5% every year, how much should she donate now? See, the thing is, $5,000 now sounds like quite a lot of money, but in 100 years' time, $5,000 is probably not going to be very much because of inflation. So she's like, actually, I want to make sure that my name attached to the scholarship is still a worthy amount long after I'm disappeared. And so, in actual fact, a lot of scholarships are exactly like this. The benefactor will say, hey, here's a big pile of money. Now, you're not allowed to touch that pile of money. That's just there to earn money. And we will make scholarship payments, etc., out of the money that it earns. But hey, hang on a minute, you can't pay all of it out either. All of that money that you earn that year, you can't pay all of that out, because what we want to do is we want to take some of that money that we earned and reinvest it. So what that does is it starts growing this pool of money. And so the bigger the pool of the money, the more money it makes, and therefore the bigger the scholarship payment can be each year. So how much will she now have to deposit? Well, it's $500,000 is the first payment that is made out of the scholarship, divided by the return of 5% less what she wants it to grow by each year, 2.5%. So now she's going to have to deposit $200,000. So let's have a look and see what's going on with her money there. So we're just going to run through sort of the first 3 years, and you'll see that it would continue on to infinity. But for the first 3 years, opening balance, and we're going to add the interest that's earned in that first year, less the payment. That's the scholarship payments, giving us a closing balance. Right, and here is Excel. So what we want is her opening balance of 100,000 equals interest is going to be, and the interest in the first year is going to be, okay, you donated 100,000, on that you're earning 5%, $5,000. And so I'm just doing the first example where she's put in $100,000. The scholarship in the first year is $5,000 as well. So our closing balance is going to be equal to what she donated plus the interest that's been, or the income that's been generated on that money that's been donated. Actually, I'll just... always can be a bit confusing if you've got double negatives and whatever, but that makes more sense now when I go through it. So start off with 100,000, earns a bit of income, but then the first payment is made out of that scholarship. So left with $100,000. That becomes the opening balance in year 2. And actually, can I just copy that across? So you can see there that all of that's happening is the income that's earned on the donated money is entirely taken out and paid out as scholarships. But the original 100,000 stays intact. That means every year it can continue to earn more income. And that's why it's a perpetuity. As long as the capital amount remains intact, it's going to continue to earn every year. What about the second example where she chucks in 200,000? Interest is going to be $10,000. Payment in the first year is going to be still $5,000. The closing balance now, though, is $205,000. That'll become the opening balance here. Interest. Earnings, you see that? She's earning now a little bit, well, this fund is earning a little bit extra interest. Our payment, though, is going to be 2.5% bigger. So what we need to do is we need to take the first year's payment and grow it by 1.025 for an extra 2.5%. Oops, that's not what I want to do. I want to copy that formula across. So you can see what's happening is that the amount of money that's invested is growing. And that's the only way that you can grow these scholarship payments, is if the pool of money that they are coming from is growing at the same time. And in fact, if you worked out, we know that this is growing by 2.5%, but if you worked out what the growth rate in the fund between year 1, year 2 and year 3 is, it's 2.5% as well. So we want to grow the payment by 2.5%, we're going to have to grow the amount, this pile of money, by 2.5% as well. And that allows them to do this extra payment. Any questions on that? Perpetuity is difficult to get your head around because it's, well, infinity is hard to get your head around, I guess. The actual calculations themselves, the present value calculations, relatively straightforward. Very few numbers involved. But the conceptual understanding behind them just takes a little bit to get your head around. So there's a couple of things that I want to finish off with, which is more applications of these time value of money formulas. The first one we're going to look at is something called cap rates, which is something that's used in the property industry. So when you're comparing different commercial properties, they'll say, oh, the capitalisation rate on this property is, it's 5%, or this one over here is 6.5%, or whatever it is. So what does that mean? Actually, it's based on these perpetuity formulas. The other thing I want to look at is an application to value things called bonds, which pulls in a couple of the previous formulas we've looked at. So in practice, so the second point here, in practice property values are estimated on the asset itself, which seems so obvious, but what this really means is that we're not looking at it from the investor's perspective with these capitalisation rates. We're looking at it from the property perspective. Because every investor will have a different tax rate. Individual investors have different marginal tax rates. If it's a company, they'll have a different tax rate. Trust owns it, a different tax rate again. So there's all these different things going on. So we can't look at it from the investor's perspective. The other thing is, the amount of money that I need to borrow might be a heck of a lot more to buy the same property than what you need to borrow. And so my interest expense will be different, because I have to borrow more. So what this means is that when you're applying this capitalisation rate, it's actually before interest costs and before any taxes. In other words, it's before all the stuff that affects me. It's just the stuff that relates to the property itself, the asset itself. So it's the net income, not my personal net income, but just the net income for the property, before taxes and before my interest expense. The required return is referred to as the capitalisation rate. So let's just see how this translates to value, then we'll look at it the other way, because it's normally the R figure that's talked about in industry. Continuing with the K's, Carl is considering the purchase of a commercial property which has net income before tax and interest of $26,000 per annum and a required return of 8%. Use the capitalisation method to estimate its market value. So the net income, $26,000 divided by R, 0.08. So it's just 26,000 divided by 0.08. You'll see that that's the perpetuity formula, right? The net income is like the cash flow. Every year this property is generating $26,000 in cash flow, or net income. And it's divided by R. So that gives us a value for the property of $325,000. However, in most cases, this, when it's applied in practice, they are talking about the R figure, the 0.08 or the 8%. They're saying, oh, this property over here has got a cap rate of 6%. This one over here is 6.5. So it allows them to compare the returns that different properties are giving. So, for instance, Carl may know that it's for sale, for instance, for $325,000. So he knows it's for sale for $325,000. He can work out what the net income will be, because those, when you buy a commercial property or something like that, or even just a residential property, you can work that out. Typically, the real estate agent for a commercial property will be providing that information to you, and so you can work it out as just it's been rearranged. Now R is just rearranged this formula as net income of $26,000 divided by the sales price, or what the vendor is asking, $325,000. So now it's like, oh, that's 8%. We look at another commercial property that's also for sale. We could buy that one. That's giving us 8.5%. So it gives us something to compare between different properties or different investments. So that's an application of those perpetuity formulas. We are going to look at an application of both the single cash flow formula from last week and also the annuity formula from this week. So bonds, we touched on this in the workshop last week where we went through, looked at the NZX and looked at several different types of bonds. And there was a whole lot of terminology which we'll talk about here as well. Face value, coupon rates and those types of things. So a bond, as we saw in week 2, is a long-term debt instrument. As we saw last week in the workshop, pays a regular coupon amount, which is interest. That's the interest payments that you get as an owner of these bonds. And the principal amount, that's the amount, is repaid when it matures. So that's all the terminology. That's called face value as well. So last week we looked up face value. When it matured, that's how much you would get back from the company, not the current price. This here, by the way, is a bond certificate. It's the oldest one I can find. I don't know whether there was too many older than this, because it's around about the same time as when it's by the Dutch East India Trading Company, which was one of the first companies to, well, was the first multinational company, and the first company really to have its shares bought and sold in the Amsterdam coffee houses, which started the original stock exchange. This one was issued on 7th November 1623, so nearly 400 years ago, and it was for 2,400 florins. The rest of it I can't read. So bond features, coupon payments, that's the interest that you get by owning one of these things. Or from the company's perspective, that's the interest they have to pay. And it's calculated as a percentage of the face value. And face value, as the next point says, is that's the amount that has to be repaid when it matures. A little bit like your term deposit. Chuck some money in the bank, gives you some interest, and then at the end, when a term deposit matures, you get your money back. So a bond's price today is the present value of all future payments received by the bondholder or the investor. And that's how they're valued. You're simply working out the cash flows that you would get as a bondholder and then applying those present value formulas. So when they're first issued by the corporation or the government, that's the primary offering of that. Later on, as we saw last week in the workshops, we can then, or investors can then trade these, just like they trade shares. And that's the secondary market. Prices in the secondary market can change based on changes in current interest rates and risks. So I've just got an example here. A few years ago, there was a bit of a scare with Fonterra that there was a botulism scare, one of its factories. So it produced this whey protein, and they thought it had botulism or an organism in it that could lead to botulism. Very serious, very bad news. It was released on the Saturday after the market was closed. The stock market's not open, the bond market's not open. And on Monday, trading can begin on that company. So again, if you think about the formulas that we've gone through, it's how's this going to, investors assessing how this piece of information is likely to impact on the future cash flows, on the risk of those cash flows and the timing of them. And actually all three of those were affected by this particular announcement. We did know very early on that Danone, a big French company, were suing Fonterra for this, and actually they achieved, I can't remember what it was, $100 million or something. And it was not an insignificant amount anyway, but they went through the court cases and won just recently. But it's also affect sales, you know. This is a reputable company that's all of a sudden people are a bit scared of buying their product, so that could affect them. Timing. Any product in parts of the world was just embargoed. It sat on the port for a long, long time before it was released. So Sri Lanka particularly, they had a whole lot just sitting in their different ports, didn't go anywhere for 6 months. And so obviously the customers weren't going to pay for something they hadn't yet received. And the risk, we didn't know how big a problem this was. Was it systemic right throughout the company? Was it just on one particular factory? We didn't know. So, not good news. What do you think happened to the share price on Monday? Yeah. Fell by 9% in the first 8 minutes of trading. What about bonds? Do you think they went up or down? Is this good news for the bondholders? It's not good news for anyone, right? So you would expect the bond price to also fall. But here's the thing, and I sort of touched on this last week. When you buy and sell bonds, you don't actually buy and sell on the price. I know you've got to pay the money eventually, or you receive the money if you're selling, but you actually trade on the return that investors want. So this is a whole heck of a lot of extra risk here now, right? New investors on Monday should want a higher return than new investors did on Friday when they didn't know about this problem. Now there's a whole lot more uncertainty. They should want a higher return to compensate for that uncertainty, and we'll look at that much more closely next week. And so what you actually have, the Fonterra bonds, their required return when they traded went up. And as we'll see, we might not have, we should be able to go through it. As you'll see, as the required rate of return goes up because of higher risk, the value goes down. Okay, so higher risk leads to lower values. So we're going to run through, we might not get all the way through, but we've still got about, another 3 or so minutes. We'll definitely get through this slide anyway. And the rest of it I can finish off next week. So calculate the value of a 5-year 9% coupon bond issued by Cooks. The par value of the bond is $100, and bond investors require 9% return for current market conditions. So what do we know? Well, they want 9% or 0.09, and N is 5. That's the first 2 bits of information. We can also work out what the annual interest is. So from the previous slide, it said it was the coupon rate multiplied by the par or face value. So par and face value, same thing, different. This old terminology, depending on which jurisdiction it's from, comes up with different terminology, but they mean the same thing. So 0.09 is the interest rate, or the coupon rate I should say, times $100 equals $9. So if you buy one of these, hand over $100 today, you're going to get $9 each year for the next 5 years. And then you'll get your money back. So there's 2 9% here, but they go in different places. So first of all, the coupon rate, think of the coupon as C for cash. Remember, if you're in the workshop, it's the things you rip off, post, and back comes money. It's the coupon rate multiplied by the par value. That's the cash flow component. So on a timeline, we've got 5 years. Every year we're going to receive $9 in interest. There is one other cash flow that we get as the bondholder, and that's our money back in year 5 when it matures. And that's the principal amount, or face value. This face or par value. So, what we are trying to do is figure out what the present value is of each one of these. The $9, second year's $9, third year, fourth year, and in the last year we received not only the $9 in interest, but also the $100 there. Time to work this through. I won't cover the last slide though. Calculating the bond value. Looks pretty nasty, but actually it's just 2 formulas that have been plonked together from chapters 4 and 5. The chapter 4 one is the bit out the right hand side, and that's just the present value of a single cash flow. What that is saying is this $100, it just happens once in 5 years' time. So we're just going to apply that formula to value that $100. But the $9 each year for 5 years, that's an annuity. It's the same every single year. So we're just going to grab the annuity formula. That's the first part of it. That's all it is. It's just put together like that. Sorry, there was one more slide. I won't cover the last one as I promised. I just want to cover through. So the annuity part of it, the face value part of it, and then we can go through the calculation of it. I'm just going to plug the numbers in so you can see that. So, the formula, wherever R is in the formula, it's 0.09. Wherever N is in the formula, it's 5 for 5 years of the bond. And the only other 2 bits of information you need is the cash flow parts. So payment for the interest payment each year of $9, and the future value, what you get back, is the $100 face value. If you calculate that all through, you'll see you get $100. That's because you require 9%. It's actually giving you 9%. It's exactly like a 5-year term deposit. On a 5-year term deposit, most banks will, after each year, they'll pay you out your interest. So you'll get $9 in interest in the first year, 9 in the second, and so on. And eventually you get your $100 back at the end. So it's no different to that, because what it's giving you is what you want. You want 9%, it's giving you 9%. At the beginning of the lecture next Thursday, I'll show you what happens if you actually want something different, or the market, everybody out there wants something different than 9%, and how that impacts on the value. Thank you very much for your patience. I know that was a lot of numbers and formulas. Thank you. We'll see you next week. So this one is where the payment is at the end of the year,
Yeah.
whereas an annuity due, where did you point to? This one, annuity due payment is the beginning, first payment at the beginning of the year.
Oh, the first payment at the beginning of the year.
Yep. Yep. So this one, end of the year, and all the formulas are generally set up so that they treat the first payment at the end of the year.
Yeah.
But this one, we have to adjust the formula. It's the same formula, right?
Yeah.
But it's just got this little bit on the end, and that converts the formula into thinking, oh, the first payment's not end yet. Yeah, right at the very beginning.
Okay. Thank you very much.
Okay.
I was just wondering why, you know how you have the lecture slides on the screen, they seem to miss some of the information or what you do on the...
That's because I generally update those examples or something like that, so that allows me to provide.
Yeah. Yeah, it's just because some of them, like you say, like you have the example and you have the answer, but you don't like show the working of how it was.
So that's so when
Like just when you like download the PDF of your slides that you make.
so you might have the formula and the answer, but none of the workings.
No, yeah.
So
it's just
that's-
like methods all the blue stuff in blue. Yeah.
So there were certain times that I stopped and did other things, and that was when I was expecting you to go through and work through.
Yeah.
And
But
then
I
you
was
go
just,
back
like,
and check.
thinking for like revision in that, it's just a little bit.
So in the recordings, you can see the whole lot.
Oh, can you?
Yeah, in the recordings,
I
though.
also recording a work bin.
Yeah, so in the recordings, it basically captures everything. It captures the screen.
Oh, okay.
So that's why I was like, when I do it on here,
Yeah.
it's also capturing that as well,
Yeah.
step by step.
Oh, okay. So if we
So you can
wanna-
go back and check if you need to.
Cool. Thank you very much.
And so this is the target for cash flow.
That's the cash flow.
Yeah, and then I still don't understand why if this is our present value, if we increase it.